Moving on to some applications of differential calculus. The first one will be optimization. Again, a nice word, but you need to realize that optimization is all about finding maxima and minima. And we already know how to do that for functions. So the whole process of optimizing something, say finding the minimum cost of production of something, is basically expressing this cost as a function of one variable and then finding the solution to the equation where the function's derivative is equal to 0. So we'll just go through one example of a question like this. There isn't going to be much new theory, much new stuff, because as I said, we already know how to do this, but I wanted to distinguish between this specific type of questions because of how popular it is and how simple yet useful application of differentiation this is basically. So here we have some 3D shape, a cylinder. It has a radius, it has a height, and we are told, we're given a constraint that its total volume is 20 pi centimeters cubed. And our goal in this question will be to optimize the cost of this cylinder, so to minimize the total amount of money we need to pay for the material if we wanted to construct such a cylinder. So all we need for the purpose of this calculation is a function for cost in terms of one variable which we can relate to the amount of material. And in this case, they will want us to do that in terms of r, in terms of radius. And in those types of questions, they always give you some sort of constraint. Yeah, in this case, this is the volume of the cylinder, with which we can actually make sure that there is one variable based on which we can express everything. So we're given h and r, but thanks to this constraint, we can connect these two and express one in terms of the other. And the material in question refers to the material for the outer surface area of the cylinder. So we will want to basically minimize the outer surface area, but taking into account the fact that the material has a different cost when it comes to the base of the cylinder and when it comes to the curved side. Okay, but I told you we need the function of one variable, and that's why they give us a constraint in these questions. They always give us a constraint first and ask to express one thing in terms of the other. And the volume of the cylinder is basically the area of the base, which is a circle, times height. So pi r squared times h, and we know that this is 20 pi centimeters cubed. Pi cancels out, and we get that h equals 20 over r squared. So now the cost of the material. Now we're creating the function whose value we need to minimize in this question. So let's look at the base and at the top first. So we know the material costs 10 cents per centimeter squared. And what's the area in centimeters squared? Well, it's pi r squared times 2. And now we need to multiply this by 10 because this is the cost per centimeter squared. And now to that, so this was our base and our top, yeah? And to that we're adding the area times the cost per unit area of the curved side, which is basically h, and h is 20 over r squared, times, yeah, the height times the circumference of the circle, which is 2 pi r. And all this is to be multiplied by 8, because that's how much a centimeter cubed of the area here on the outside costs. When we simplify all this, you can check that it indeed comes up to 20 pi r squared plus 320 pi over r. Yeah, so this is our function for cost in terms of the chosen length of the radius. Yeah, so in these examples, you want to sort of imagine that you are a manufacturer of this packaging, say, and you want to change the dimensions so that you minimize something. In this case, it is the cost of material for the walls. Yeah. So you choose one of the variables. In this case, you chose r, and you look at what happens when you change the radius. What happens to the surface area? What happens to the cost of the materials required for the packaging? And for this to make sense, there needed to be some constraint. In other words, there needed to be something that related r to height. Yeah, as you changed r, h needed to change as well so that the total volume is 20 pi centimeters cubed, because say this packaging needs to contain this many liters of some liquid. And yeah, now comes the differentiation part, the optimization, which is this simple method really. If we want to find the minimum of a function, and these questions, there will usually only be a minimum or only a maximum, so you don't need to worry about distinguishing between those, just find a stationary point and that's the one they're looking for. So a minimum value of c is what we want to find, so we want to find a stationary point of this function. What do? We find the derivative, so c prime of r, and that is going to be 40 pi r plus, this is going to be a little bit more difficult because this is r to the -1, so we will have -1 in the front, 320 pi, and r to the power of -2, and that's our derivative. So we simplify, we factor out 40 pi, and we get r minus 8 over r squared. And for some value of r, this is supposed to equal 0, because we're looking for a stationary point, we're looking for a minimum. So in other words, 40 pi times these brackets need to equal 0. So basically r minus 8 over r squared needs to equal 0. So this will be a polynomial we can multiply by r squared both sides, and we get r cubed minus 8 equals 0, r cubed equals 8, so r equals 2. That's in centimeters. So now we have found the argument, the x, for which the derivative of our function equals 0, so for which we have the maximum or the minimum value. And again, I said we don't need to worry about distinguishing between these and those types of questions, because notice how there was only one solution here. So if there was only one solution, one stationary point, and they're asking us to find the minimum, then it needed to be the minimum. And the very last bit is just plugging in this value of 2 centimeters into our function for the cost so that we get the value of this minimum cost. And this is then going to be 80 pi plus 160 pi, so 240 pi cents, because that was the unit of the cost.